Hello, and welcome to the Science for Sleep channel, a gentle corner of the universe where curiosity meets calm. If you're someone who likes to relax by thinking about distant stars, quiet planets, and the soft, endless beauty of space, then you've arrived exactly where you need to be. This is a place to slow down, to let the noise of the day fade away, and to drift into thoughts that stretch far beyond Earth. Tonight, we're leaving our familiar solar system behind. We're moving past the warmth of our sun, gliding beyond the known planets, and drifting into the deep, silent darkness between the stars. Out there, other suns glow faintly in the distance, and countless planets orbit them, worlds shaped by forces far stranger than anything we experience at home. In this vast cosmic ocean, almost anything is possible. On our journey, we'll visit planets where metal falls from the sky like rain. We'll explore worlds formed from ice and fire, and encounter enormous, lonely giants drifting endlessly through space with no star to call their own. Some of what you hear tonight may sound impossible, almost unreal, but every world we'll talk about is rooted in real scientific discovery. These planets exist. They are part of our universe, quietly orbiting distant stars or wandering alone through the darkness. And if you find yourself enjoying these slow, sleepy journeys through space, you're welcome to like and subscribe. It helps others discover this peaceful place, too. But for now, there's nothing you need to do. Get comfortable. Let your shoulders relax. Let your breathing slow. Allow your thoughts to wander freely as we begin. There are planets with temperatures so extreme that they rival stars themselves. Stars are known as the great furnaces of the cosmos, massive spheres of glowing plasma burning at millions of degrees. Yet, astonishingly, some planets come closer to that level of heat than we ever thought possible. One such world is known as KLT9b. KLT9b is a massive gas giant that reaches temperatures above 7,000 degrees Fahrenheit, making it hotter than many red dwarf stars. It orbits an enormous blue star at an incredibly close distance, completing a full orbit in just over a single Earth day. A year on this planet passes in the blink of an eye. This world is tidally locked, meaning one side of the planet always faces its star, locked in perpetual daylight and exposed to a relentless flood of radiation. The other side remains in constant darkness. The heat is so intense that the planet's atmosphere is being torn apart, stretching out into space like the glowing tail of a comet. At these temperatures, molecules cannot survive. They split apart. Metals vaporize and float as gas. This is not just heat. It is an extreme environment unlike anything in our solar system. These ultra-hot Jupiters challenge our understanding of what planets can be. They blur the line between planet and star, existing as blazing, storm-racked infernos that may only last a short time before slowly dissolving back into space. Some planets may be made almost entirely of diamond. It sounds like science fiction, but under the right conditions, it could be real. Certain exoplanets form in regions rich in carbon, where carbon is more abundant than oxygen. In these environments, the building blocks of planets can take a very different path. Instead of forming rocky worlds like Earth, intense pressure deep inside these planets may force carbon into crystalline diamond structures. One possible example is 55 Cancri e, a super-Earth about twice the size of our planet. Beneath its surface, unimaginable pressure and heat could create vast regions of solid diamond. This wouldn't be a glittering world filled with sparkle and light. There would be no shine, no beauty as we imagine it. Only darkness, heat, and incredible density. Still, the idea is captivating. A planet forged from carbon, where mountains may be built from buried crystal and geology itself becomes something rare and otherworldly. Some exoplanets orbit not one sun, but two. For decades, we imagined twin sunsets only in science fiction, like the skies of Tatooine in Star Wars. But now, we know these worlds truly exist. They are called circumbinary planets. Instead of orbiting a single star like Earth does, they move in graceful, complex paths around pairs of stars that orbit each other. When the two stars are close together, a planet can circle both of them as if they were one. When the stars are farther apart, the planet's motion becomes more complicated, pulled and tilted by the gravity of both suns. The The result is a world with shifting light patterns, unusual seasons, and skies that cast double shadows. These systems are rare and delicate, but real. Somewhere in the universe, a planet truly experiences two dawns and two dusks. A sky once imagined in fiction, now quietly confirmed by science. There are planets where it rains molten glass. Some worlds are so alien that even their weather defies imagination. One striking example is HD 189733b, a gas giant larger than Jupiter that orbits its star in just over 2 days. Its atmosphere burns at around 1,700 degrees Fahrenheit. Winds roar across the planet at thousands of miles per hour. Suspended within its deep blue, hazy skies are tiny particles of silicate, the same materials that form glass on Earth. When conditions are right, these particles condense and fall as rain. Not water, not ice, but molten glass, blown sideways by ferocious winds. From far away, the planet glows with a soft, Earth-like blue color. But up close, it is a violent storm world, beautiful, deadly, and completely uninhabitable. Some exoplanets may be ocean worlds, planets almost entirely covered in water. No continents, no islands, just endless, global seas stretching in every direction. Unlike Earth's oceans, which reach only a few miles deep, these oceans could be hundreds or even thousands of miles thick. At the surface, the water might appear calm or stormy, peaceful or violent. But far below, pressure rises to unimaginable levels, creating exotic forms of ice-dense, high-pressure ice formed under crushing weight. Beneath all that water, a rocky core may still exist, warmed by internal heat. Some layers might even remain liquid deep below the ice. Could life exist in such oceans? We don't yet know, but ocean worlds may be far more common than we once believed. Gentle, glistening planets with no land in sight, quietly turning in the dark, far from any sun we know. Some planets are tidally locked, just like our moon is to Earth. One side of the planet always faces its star, while the other remains in permanent darkness. Imagine an entire hemisphere scorched by endless daylight, while the opposite side is trapped in eternal night. Between them lies a narrow twilight zone, a ring of constant dusk where temperatures may be more balanced. Some scientists believe that if life exists on these worlds, it may survive in this thin, fragile band, thriving neither in full light nor complete darkness, but somewhere gently in between. And as you rest here, drifting through these distant worlds, remember, the universe is vast, quiet, and endlessly strange. And tonight, there is nowhere else you need to be. These planets may be shaped by fierce winds, strange and unfamiliar cloud formations, and extreme, unpredictable weather unlike anything we experience on Earth. Their climates can swing between violent heat and crushing cold, between endless daylight and eternal darkness. And yet, despite their harsh conditions, these worlds are very real. They exist, quietly orbiting distant stars, forcing us to rethink everything we believe about what makes a planet habitable. If life exists on such worlds, it may not thrive in bright sunlight or gentle environments. Instead, it might adapt to shadows, to narrow twilight zones, or to the fragile boundary between light and dark, surviving not despite the extremes, but because of them. Some of the most dramatic examples of these extreme worlds are known as hot Jupiters. Imagine a planet similar to Jupiter, massive, gaseous, and immense. A giant built mostly of swirling hydrogen and helium. Now imagine dragging that planet incredibly close to its star. So close that a full orbit takes only a few days. So close that temperatures soar beyond 2,000 degrees Fahrenheit. These are hot Jupiters, enormous planets that skim just above their star's surfaces, orbiting so tightly that their upper atmospheres are being blasted away into space. We discovered many of these strange planets early in our search for exoplanets. Their sheer size and tight orbits made them easier to detect, but they raised more questions than answers. How did such massive planets end up so close to their stars? Did they form there, or were they slowly pushed inward over time by gravitational interactions with other planets? Some hot Jupiters trail long, glowing tails of gas like cosmic comets. Others are slowly shrinking as their atmospheres evaporate, stripped away by relentless stellar radiation. These planets are unstable, dramatic, and often short-lived, brief flashes of planetary fire circling faraway suns before fading into darkness. Some exoplanets are darker than charcoal. Not all planets reflect light the way Earth does. Some absorb nearly everything that touches them, becoming darker than paint, darker than ash, darker even than coal. One of the darkest worlds we know is Trace 2b, a gas giant orbiting a star about 700 light-years away. Its atmosphere reflects less than 1% of the light that strikes it. Scientists are not entirely sure why. The darkness may be caused by vaporized alkali metals or unfamiliar chemical compounds suspended high in its atmosphere. Whatever the reason, the result is haunting. A planet nearly invisible against the brightness of its star, glowing faintly only from its own internal heat. Even its night side, already shrouded in darkness, is only slightly cooler than its blazing day side. If you could stand nearby and look toward this world, you might see only the faintest silhouette, a nearly perfect shadow drifting silently across the fire of its star, absorbing light as if it were swallowing the universe itself. We have also discovered planets that wander alone, without a star to guide them. Most planets are born around stars, bound to them by gravity, tracing predictable paths through space. But not all planets remain tied to their suns. Some are cast out, ejected from their home systems by violent gravitational encounters. Others may form alone, like failed stars that never gathered enough mass to ignite nuclear fusion. These lonely worlds are known as rogue planets. Rogue planets drift through the galaxy in complete darkness, unbound to any star. We've found evidence of dozens, perhaps hundreds, and scientists believe there may be billions of them. They are incredibly difficult to detect, but powerful infrared telescopes allow us to glimpse their faint thermal glow. Some may still retain internal heat, enough to keep subsurface oceans warm for billions of years beneath thick layers of ice. Others may be entirely frozen, drifting endlessly through the black, planets without sunrises, worlds with no sky. And yet, even here, the quiet question remains. Could something live in such stillness? Some worlds may have clouds made not of water, but of gemstones. When we think of clouds, we imagine soft shapes of white and gray drifting across the sky. But on some exoplanets, clouds may shimmer with minerals. On scorching hot gas giants, where temperatures exceed 2,000 degrees, materials that would be solid rock on Earth can vaporize, rise into the atmosphere, and condense into clouds. Aluminum oxide, iron, titanium, and in some cases, corundum, the mineral that forms rubies and sapphires. These mineral clouds scatter light in strange and beautiful ways, tinting alien skies with deep reds, purples, and glowing blues. On a planet known as WASP 7b, scientists have observed shifting atmospheric patterns that suggest high-altitude mineral clouds racing across the sky. It is difficult to imagine a world wrapped in heat and storms, illuminated by a blazing star, with clouds of liquid gemstones swirling overhead, and yet, such worlds may exist. Some planets may even be more hospitable to life than Earth. Among the thousands of exoplanets discovered, there is a class known as super-Earths, rocky planets larger than Earth but smaller than Neptune. These worlds may have stronger gravity, thicker atmospheres, and more stable climates. Some could possess deeper oceans, fewer tectonic disruptions, and long-lasting geological stability, all factors that might help life emerge and endure. One promising candidate is Kepler 442b, a rocky super-Earth located in the habitable zone of its star. It receives just the right amount of sunlight, not too hot, not too cold, and has enough mass to retain an atmosphere and possibly liquid water. While we don't yet know if it is truly habitable, such worlds remind us of something humbling. Earth may not be the perfect planet, just the one we happen to call home. We've also discovered planets that orbit their stars at astonishing speeds. Earth takes 1 year to complete an orbit. Mercury, the fastest planet in our solar system, takes 88 days. But some exoplanets complete a full orbit in just a few hours. One of the fastest is Kepler 78b, a rocky world slightly larger than Earth that circles its star every 8.5 hours. It orbits so close that its surface is likely covered in molten lava, glowing under temperatures that reach several thousand degrees. These ultra-short period planets are often tidally locked, with permanent day and night sides. Their stars dominate the sky, looming huge and overwhelming. Gravity stretches them, and some may be slowly tearing themselves apart. They are fast, fleeting, and extreme sparks skimming the edge of a cosmic flame. And while some planets race, others move at an almost unimaginable pace of slowness. Some take centuries to complete a single orbit. One such world is Geopisium b, a gas giant so distant from its star that it takes nearly 1,000 years to complete one loop. Its orbit is barely held by gravity. Any farther and it might drift away forever. These long-period planets are incredibly difficult to detect. We cannot wait centuries to observe their motion. Instead, we catch only a fragment, a curve, a gentle arc, a silent hint of something vast and patient moving through time. And as you drift through these distant worlds, remember, the universe is quieter, stranger, and far more beautiful than we ever imagined. Some of these distant planets may have cold, silent surfaces, locked in darkness and illuminated only by the faintest glow of faraway starlight. On such worlds, shadows stretch endlessly across frozen ground, and the sky may never truly brighten. Others may experience seasons that last not months or years, but entire lifetimes. On these planets, the passage of time is measured not by calendars, but by generations. Winters may endure for centuries. Summers may arrive once in 1,000 years. Change unfolds slowly, quietly, following a rhythm far beyond human experience. A deep, cosmic pulse that moves with patience and permanence. We now know that these worlds are not rare. We have discovered thousands of planets beyond our solar system. For most of human history, we believed our planetary system was unique. We knew only the sun, the moon, and the wandering points of light that traced patterns across the night sky. Everything changed in the 1990s when the first exoplanets were confirmed. Since then, our understanding of the universe has expanded dramatically. With space telescopes like Kepler and TESS watching the sky without blinking, we have now identified thousands of planets orbiting distant suns. Some of these worlds are small, rocky, and similar in size to Earth. Others are enormous gas giants, bloated and strange, orbiting dangerously close to their stars. Some complete an orbit in just a few days, racing through their years. Others move so slowly that a single orbit can take centuries. Each discovery reshapes what we believe planets can be. Each one adds a new possibility to the cosmic story. And still, this is only the beginning. Scientists believe there may be hundreds of billions of planets in our galaxy alone. More planets than stars. World after world, quietly orbiting in darkness. We may never visit most of them, but we can listen for them, measure their presence, and wonder what else may be waiting out there. One of the most powerful ways we've detected these distant worlds is by watching the shadows they cast. The light of a star usually shines steadily, but sometimes just briefly it dims. A tiny dip, a subtle flicker, almost imperceptible. That dimming can mean a planet has passed in front of the star. This technique is known as the transit method. When a planet crosses its star from our point of view, it blocks a small fraction of the starlight. The change is delicate, often less than 1%, but with precise instruments it can be measured. Space telescopes like Kepler and TESS have used this method to discover thousands of exoplanets. From these faint shadows alone, scientists can determine a planet's size, its orbital period, and even clues about its atmosphere. We are watching stars blink ever so slightly to learn about unseen worlds. Distant suns briefly interrupted by the quiet silhouette of a planet passing far away. Other planets have revealed themselves through gravity. When a planet orbits a star, it doesn't simply circle around it. The planet's gravity pulls back, causing the star itself to wobble slightly. This movement is incredibly small, but it leaves a detectable signature. As the star shifts, its light is subtly stretched and compressed. Astronomers can measure this effect using spectroscopy, breaking the starlight into its component colors and searching for tiny changes that indicate motion. This technique is called the radial velocity method, and it was how the first exoplanets were discovered. This method works especially well for large planets close to their stars, such as hot Jupiters, but it has also helped uncover complex multi-planet systems and long-period orbits. We are not seeing the planets directly. Instead, we watch their stars sway, like a distant dance we cannot see, but can feel through the music of light. Some exoplanets appear to be losing their atmospheres to space. A planet's atmosphere is never completely still. Winds blow, clouds drift, and particles slowly escape. But in extreme cases, the entire upper atmosphere may be streaming away, leaking into space like breath into the void. This often happens to hot, close-in gas giants, where intense radiation from the nearby star heats the atmosphere until it reaches escape velocity. These planets can develop long, comet-like tails made of hydrogen and helium, stretching far behind them as they orbit. Astronomers have observed these glowing trails in ultraviolet light, watching gas flow away into space. Over time, some planets may lose a significant portion of their mass. Others may be stripped down entirely, leaving behind only rocky cores. This process shapes planetary systems, showing how stars can sculpt, reshape, and even destroy their planets. It is a reminder that worlds are not permanent. They evolve, erode, and sometimes fade away, leaving only gravity and memory behind. We have even found planets in systems with 3 or more suns. Not every star system is simple like our own. Some contain 2, 3, or even more stars bound together by gravity. In a few of these complex systems, planets still manage to exist. Imagine a world where the sky is never still, where one sun rises as another sets, where shadows stretch in multiple directions and darkness never fully arrives. These planets must follow incredibly delicate and stable paths to survive the tangled gravitational pull of multiple stars. Some orbit closely around pairs of stars as circumbinary planets. Others orbit far beyond the entire cluster, tracing vast loops around a chaotic center. Their skies would be full of motion, their seasons unpredictable, their light ever-changing. And yet, these planets exist. They remind us that planetary systems can form even where gravity is complicated, and that nature often finds a way. Some worlds orbit the collapsed remains of dead stars. Stars do not live forever. Some end as white dwarfs, small, dense embers left behind after a star like our sun exhausts its fuel. Others collapse into neutron stars or vanish into black holes. Around some of these stellar remnants, planets still remain. In some cases, they survived the violent death of their star. In others, they may have formed afterward, emerging from the debris like worlds reborn from ashes. These planets orbit dim, distorted, or pulsing remnants of stellar fury. Some are blasted by radiation. Others drift quietly in eternal twilight, circling dead suns through silent stellar graveyards. It is haunting and beautiful, a reminder that even after endings, something strange and new may begin again. And finally, we have found at least one planet that orbits its star backwards. Most planets orbit in the same direction their star spins, forming from a shared disk of gas and dust. But the universe does not always follow the rules. Sometimes, gravity twists systems into unexpected shapes. Even here, among the stars, nature allows for rebellion, and the cosmos continues to surprise us. We have discovered at least one extraordinary exoplanet, known as WASP 17b, that moves through space in a way that seems to defy the natural order. Instead of orbiting its star in the same direction that the star itself rotates, WASP 17b travels the opposite way, pushing against the flow rather than following it. This backward or retrograde orbit likely formed through chaos long ago, perhaps a near collision with another planet, a powerful gravitational shove, or a violent rearrangement within its original planetary system. Whatever caused it, the result is striking. WASP 17b is massive, bloated, and intensely hot. It orbits extremely close to its star, completing a full circuit every few days while enduring relentless radiation. Its strange motion challenges our understanding of how planetary systems form and evolve. It reminds us that gravity can twist worlds into unexpected paths. The universe is not rigid or orderly in the way we often imagine. It is flexible, chaotic, and endlessly surprising. Some planets move with the current of cosmic motion. Others resist it, and some, like WASP 17b, drift through space with quiet defiance, proving that even planets can rebel. We have also seen signs of clouds on planets light years away. At first, this seems impossible. These worlds are too distant to photograph in detail, too faint to observe directly. And yet, through careful study, scientists have detected evidence of clouds on exoplanets dozens and even hundreds of light years from Earth. This is done by observing what happens to starlight as a planet passes in front of its star. During this transit, a thin layer of starlight filters through the planet's atmosphere before reaching us. As the light passes through that alien air, certain wavelengths are absorbed while others scatter or slip through untouched. This creates a delicate fingerprint, a subtle pattern hidden within the light itself. From that fingerprint, scientists can infer the presence of gases, molecules, and tiny particles suspended in the atmosphere. In several cases, the data suggests clouds. Not soft, white clouds like those drifting above Earth, but dark, metallic, or mineral-based clouds made of silicates, iron vapor, or exotic chemical compounds. These clouds may blanket entire planets, permanently covering their skies. Others may form shifting patterns, changing with altitude, temperature, and wind. Some reflect starlight, others trap heat, shaping the planet's climate in dramatic ways. We cannot yet see these clouds directly, but we can read their presence from starlight alone, learning the weather of distant worlds without ever seeing their skies. Some exoplanets orbit even closer to their stars than Mercury does to our Sun. Mercury is already a scorched, airless world, stripped down by heat and radiation. But many exoplanets exist at distances where no planet in our solar system could survive. These worlds race around their stars in mere hours or days. Their surfaces may be oceans of molten rock. Their atmospheres may be blasted away by stellar winds. Many of these planets are tidally locked, with one side permanently facing the star, glowing under endless daylight, while the other side remains frozen in eternal night. Others are so close that gravity stretches them, pulling them into distorted shapes, elongated like teardrops by the star's powerful tidal forces. These extreme planets challenge every assumption we hold about habitability. And yet, they were among the easiest to detect, which is why many of the first exoplanets discovered belong to this category. They are hot, unstable, and short-lived, but they reveal just how extreme planetary systems can be. At the opposite extreme are planets that drift far beyond the reach of warmth and light. Not all planets cling closely to their stars. Some orbit at such vast distances that sunlight becomes little more than a faint glow in the sky. These distant worlds may take hundreds or even thousands of years to complete a single orbit. Temperatures plunge. Seasons stretch across generations. Chemical reactions slow almost to a halt in the deep cold. Yet even here, planets persist. Silent and patient, they circle at the very edge of gravity's reach. Some may be icy giants wrapped in frozen clouds. Others may be rocky and barren, crusted over with ice, carbon dust, and frozen gases. And some may still hold warmth deep beneath their surfaces, heat generated by radioactive decay or trapped from the moment of their formation. These far-flung worlds are difficult to detect, but their existence reminds us that planets can survive in places once thought empty. Even in the loneliest reaches of space, a world can quietly endure. There are also planets that may possess ring systems far more spectacular than anything we see around Saturn. Saturn's rings are graceful bands of ice and dust, delicate and bright, but they may not be the most impressive rings in the universe. Some exoplanets appear to be surrounded by enormous ring systems, stretching across vast distances, so wide they could eclipse their host stars. One candidate is J1407b, a giant planet or brown dwarf that may be encircled by a ring system more than 200 times larger than Saturn's. These rings could be composed of ice, rock, or dust, possibly the raw material from which moons are forming. As the planet passes in front of its star, the rings cast complex, deep shadows, creating strange and dramatic dips in the star's light. If such a planet existed in our solar system, its rings would dominate the night sky, stretching from horizon to horizon. These rings remain hypothetical for now, but their shadowy signatures hint at grandeur still waiting to be confirmed. Despite everything we've learned, we are only just beginning. The first confirmed exoplanet discovery was made in 1992. In cosmic terms, barely a heartbeat ago. Since then, our technology has advanced rapidly. Thousands of planets have been found, and thousands more await confirmation. We have detected atmospheres, measured sizes and orbits, and traced alien skies through light and shadow. And yet, we still know so little. We cannot see their surfaces clearly. We do not know what they smell like, what they sound like, or what it would feel like to stand upon them. We do not yet know which ones have oceans, continents, or life. Every new exoplanet is a doorway into the unknown. And as our instruments grow more sensitive, the picture will only become stranger, richer, and more filled with wonder. The cosmos is full of planets, and we have only just knocked on the door. Some planets orbit so close to their stars that they are slowly being destroyed. For these worlds, proximity is not just dangerous, it is fatal. Intense radiation heats their atmospheres until they expand and escape into space. Stellar winds tear particles away, forming long, glowing tails of gas that trail behind them like comets forever fleeing their suns. One such planet, K2-22b, may be actively disintegrating. With each orbit, dust and debris appear to stream away from its surface, as if the planet itself is crumbling. It is a slow, relentless erosion, a world dissolving grain by grain. These planets remind us that worlds are not static. They are dynamic systems, constantly reshaped by their environments. Even something as massive as a planet can be worn down by light alone. Again and again, the universe defies our expectations. Just when we think we understand planets, new discoveries overturn our assumptions. We have found worlds where skies shimmer with vaporized metal, rocky planets hotter than lava, and gas giants colder than the depths of interstellar space. We have seen tilted orbits, backward spins, and rings vast enough to blot out stars. Some planets are impossibly dense. Others are puffed up and fragile. And with each discovery, the message becomes clearer. The universe is not finished surprising us. Others are far too fluffy, strangely inflated, and unexpectedly fragile. Some exoplanets appear as though they shouldn't exist at all, at least not according to the planetary models we've relied on for decades. Our equations suggest they should collapse, evaporate, or never form in the first place. And yet, there they are, hanging silently in space, real and undeniable. Every discovery like this forces scientists to pause and reconsider how planets are born, how they survive, and how wildly nature can bend its own rules. Science grows strongest in moments of surprise. In the vast chaos of the cosmos, order is only part of the narrative. The rest is written in anomalies, edge cases, and quiet contradictions. Small cosmic puzzles scattered across the galaxy, waiting patiently for someone to notice them and ask why. Some exoplanets may be true water worlds, planets with no land at all. Imagine a world without continents, without mountains or beaches, no islands breaking the surface, no shorelines marking an edge, just endless oceans stretching in every direction. These water worlds could be entirely covered by liquid water, not shallow seas like those on Earth, but global oceans hundreds or even thousands of miles deep. Beneath the surface, pressure would rise to unimaginable levels, compressing water into exotic high-pressure forms of ice and crushing rock into unfamiliar structures. Above, thick atmospheres rich in steam could swirl endlessly, forming vast cloud systems and hazy skies. Some may be warmed by sunlight, others by internal heat trapped deep within. If life exists on such worlds, it would likely evolve far from light, shaped by chemistry, currents, and heat rather than day and night. We haven't confirmed a true water world yet, but the evidence continues to grow. And if Earth represents one version of habitability, then perhaps these dark, global oceans represent another entirely. We've also found a vast population of Neptune-like planets, small yet swollen with gas. Not every planet fits neatly into the categories we once believed were universal. Between Earth and Neptune exists a mysterious class known as mini-Neptunes. These worlds are larger than Earth but smaller than our ice giants, often wrapped in thick layers of hydrogen, helium, and other gases. Beneath those clouds may lie rocky or icy cores, deep oceans, or environments unlike anything we've imagined. Some may host boiling seas hidden beneath crushing atmospheres. Others may lack any solid surface at all. For a long time, scientists weren't even sure planets like this could exist. Now we believe they may be the most common type of planet in the galaxy. Strange, swollen, and still deeply mysterious, they fill the gap between expectation and reality. Some planets are puffed up like cosmic balloons. These so-called puffy planets are enormous in size but surprisingly low in density. Huge, soft worlds that could theoretically float in water if such a thing were possible. One striking example is WASP-17b, a gas giant nearly twice the size of Jupiter but with only a fraction of its mass. These planets likely formed far from their stars before migrating inward. Once close, intense stellar radiation caused their atmospheres to heat, swell, and expand. In some cases, gas escapes entirely, forming long, ghostly tails trailing behind the planet. We still don't fully understand why these worlds are so inflated, but they reveal that planets are not rigid objects. They are elastic, dynamic systems shaped by heat and light. There are also exoplanets where a single day lasts longer than an entire year. On Earth, we rotate once every 24 hours and orbit the Sun in 365 days. But some planets orbit their stars so closely that their year passes before they complete a single rotation. These planets are often tidally locked, with one side permanently facing their star. The day side burns under endless daylight, while the night side remains frozen in eternal darkness. There is no sunrise, no sunset, just a permanent divide between light and shadow. On such worlds, time itself feels distorted. A day that never ends. A year that races by. Some worlds may be hidden beneath thick, hazy skies. While we often imagine alien planets with crystal clear views, many exoplanets are wrapped in dense layers of haze made from complex hydrocarbons, photochemical smog, or exotic cloud particles. On Earth, we see something similar on Saturn's moon Titan, where golden fog conceals the surface entirely. On exoplanets, ultraviolet light from their stars can trigger chemical reactions high in the atmosphere, building murky layers that scatter light and trap heat. From space, these planets appear muted and soft in color. Yet beneath the haze, oceans may churn, winds may roar, and alien landscapes may lie hidden. We've even seen evidence of winds whipping through alien skies at unimaginable speeds. Weather doesn't belong to Earth alone. On some exoplanets, especially massive gas giants locked in permanent daylight, temperature differences drive winds faster than anything in our solar system. Astronomers have detected winds reaching up to 5,000 miles per hour, fast enough to cross continents in minutes. These winds can move clouds, redistribute heat, and carry vaporized metals through the atmosphere. Some even shift where the planet appears brightest, altering how light escapes into space. The motion itself is invisible, but written into the planet's glow, a faint signature of storms raging far away. And finally, not all heat comes from a star. Some exoplanets may be warmed from within. Planets on stretched, eccentric orbits can experience powerful tidal forces that knead their interiors, generating heat through friction. These worlds may glow internally, shaped as much by gravity as by sunlight, reminding us that planets are living systems, constantly changing, constantly responding to the forces around them. As these planets move through shifting gravitational forces, their interiors are constantly stretched and squeezed. This slow but relentless flexing creates friction deep beneath their surfaces, generating heat from within. It's the same process that keeps Jupiter's moon Io violently volcanic, its surface reshaped by lava flows and eruptions driven not by sunlight, but by gravity itself. And this process doesn't stop with moons. Exoplanets too, especially those orbiting close to massive stars or caught in complex gravitational dances with neighboring planets, can experience intense tidal heating. Over time, this internal stress can melt solid rock into magma, or keep vast subsurface oceans warm and liquid beneath thick shells of ice. From the outside, these planets might appear frozen, dark, or lifeless. But inside, they may be alive with motion, heat, and change. Energy without sunlight, activity without a star's warmth. It's a powerful reminder that planets don't need to sit in perfect light to remain active. Even in the cold outskirts of a system, a world may still burn quietly from within. We've also discovered planets orbiting some of the oldest stars in the galaxy. These ancient stars formed during the universe's earliest chapters, when heavy elements were rare and galaxies were still taking shape. And yet, around a few of them, planets endure. One remarkable example is the Kepler 444 system, more than 11 billion years old, hosting 5 small rocky planets. These worlds formed when the universe itself was young, built from materials very different from those that formed Earth. They've survived billions of years of stellar flares, galactic tides, and cosmic upheaval. What might such planets look like after all that time? Their surfaces may be worn smooth by relentless impacts, their interiors cooled or reshaped by eons of geological activity. Could they have once hosted life, long before life appeared on Earth? We may never know, but these ancient planetary systems remind us that planets can persist far longer than civilizations, species, or even oceans. They are cosmic elders, quietly circling through deep time, still here, still moving. Some exoplanets may also have moons, entire companions we've yet to clearly see. Where there are planets, moons often follow. Yet, despite discovering thousands of exoplanets, confirmed exomoons remain elusive. They are small, subtle, and easily lost in the noise of distant measurements. Still, astronomers have seen hints. Tiny irregularities in transit timing, unexpected dips in brightness, gentle wobbles that don't quite match existing models. One possible candidate, orbiting the gas giant Kepler 1625b, is still under investigation. If confirmed, it would be enormous, larger than any moon in our solar system. But even smaller exomoons could be significant. They might stabilize planetary climates, shape tides, or create sheltered environments where life could persist. Some could harbor subsurface oceans like Europa or Enceladus. Others might be rocky, cratered worlds drifting through eternal twilight. We haven't seen them clearly yet, but chances are they're out there, circling silently, waiting to be discovered. Some exoplanets may host entire systems of moons. Just as planets orbit stars, moons orbit planets, and massive gas giants could support dozens or even hundreds of moons. In our own solar system, Jupiter and Saturn each host sprawling moon families, ranging from tiny captured rocks to massive worlds with oceans beneath ice. Now imagine a gas giant far larger than Jupiter orbiting a distant star. It could possess a miniature solar system of its own. Some moons might be icy, others rocky. A few could lie within habitable regions around their parent planet, shielded from harsh stellar radiation and warmed by tidal forces. While none of these systems have been confirmed yet, the possibility alone expands our understanding of how many worlds may exist. Not just planets, but entire families of them. Some exoplanets may support life, but not as we know it. When we imagine alien life, we often picture familiar conditions. Liquid water, moderate temperatures, breathable air. But life may not need any of those things. Some worlds could host life in acidic clouds, beneath ice-covered oceans, or within dense methane-rich atmospheres. Life might not even rely on water, carbon, or DNA. On Earth, extremophiles already thrive in boiling acid pools, radioactive caves, and deep-sea vents without sunlight. If life can adapt here, then on distant worlds it may take even stranger forms. Not creatures we'd recognize, but microbial networks, chemical ecosystems, or self-replicating systems thriving in environments we'd find lethal. We may never encounter them directly, but one day, we might detect a subtle imbalance in an atmosphere, a chemical whisper suggesting something is alive. We've also found planets that barely qualify as planets at all. There is a thin, blurry line between planets and stars, and some exoplanets sit right on that boundary. These objects, often called superjupiters or brown dwarfs, are massive enough to fuse small amounts of deuterium in their cores, yet not massive enough to sustain full stellar fusion. They glow faintly with leftover heat from their formation and emit infrared light into the darkness. One such object, HD 100546b, may exist right at this threshold, blurring the line between a planet and a failed star. Scientists still debate where the cutoff truly lies. These in-between worlds remind us that cosmic categories are rarely clean. In space, one thing often slowly becomes another. Some worlds lie right on the edge of the habitable zone. Often called the Goldilocks zone, this region marks where temperatures could allow liquid water to exist. But many exoplanets sit at its uncertain boundaries. Too far out and water freezes solid. Too close in and it boils away. On the edge, conditions depend on atmosphere, pressure, and internal heat. A thick atmosphere might trap warmth. Internal heating might stabilize oceans. These worlds live on a knife's edge between frozen and burning, reminding us that habitability is not a single line, but a spectrum, and that life, if it exists, may cling to the margins. A planet's reflectivity can dramatically shape its fate. A highly reflective surface or atmosphere, covered in ice, clouds, or bright minerals, can bounce much of a star's energy back into space, keeping the planet cooler than expected. On such worlds, even proximity to a star doesn't guarantee warmth. Add seasonal shifts or a stretched, eccentric orbit, and the climate can swing violently. One hemisphere might briefly become temperate and habitable, while the other remains locked in searing heat or deep freeze. Life, if it exists at all, might survive only in narrow refuges, beneath thick ice sheets, deep within caves, or clustered around volcanic vents where heat leaks from below. These boundary worlds are not fully welcoming, but not entirely dead either. They exist in a state of tension, balanced delicately between extremes of warmth and cold, light and darkness. Here, habitability is fragile, always on the verge of tipping, yet sometimes holding on just barely. We are now learning how to read the chemistry of alien atmospheres. Until recently, the idea of studying the air of a planet light years away sounded like science fiction. But today, with instruments such as the James Webb Space Telescope, it has become reality. When an exoplanet passes in front of its star, a small fraction of starlight filters through the planet's atmosphere before reaching us. That light carries subtle fingerprints, spectral lines left behind by gases in the air. By breaking the light into its component colors, scientists can identify molecules like water vapor, carbon dioxide, methane, and even more complex compounds. From these clues, we can infer pressure, temperature, cloud layers, and atmospheric structure. In rare cases, we may even detect biosignatures, chemical imbalances that hint life could be influencing the atmosphere. It's like receiving a coded message from across the galaxy, written not in words, but in light. We're only beginning to decipher these signals, but with every spectrum analyzed, alien skies become a little less mysterious. Some exoplanets may experience seasons that last decades or even longer. On Earth, seasons are shaped by a modest axial tilt and a stable orbit. But on distant worlds, the mechanics can be extreme. A planet with a dramatic tilt, an elongated orbit, or multiple stars could experience summers that last for decades and winters that stretch across entire lifetimes. Such a planet might swing close to its star, warming dramatically for a brief era, only to drift far away into centuries of frozen darkness. Others may endure chaotic, unpredictable seasons that change with every orbit. Life, if present, would have to adapt to rhythms unlike anything we know. Entire generations might live and die within a single prolonged spring. The passage of time itself would feel different, measured not in days or years, but in slow celestial arcs and distant stellar dances. Some worlds may never experience true day or night at all. On tidally locked planets, one side always faces the star while the other remains in permanent darkness. Between these extremes lies a narrow band called the terminator, a ring of eternal twilight. In this region, the sky glows dimly forever, suspended between blazing daylight and endless night. Temperatures here could be more stable, winds gentler, conditions less extreme. If life exists, it may flourish along this narrow boundary, tracing a thin line around the planet where light and shadow meet. There would be no sunrise or sunset, only a star fixed forever on the horizon. A world where time drifts in half-light and nothing ever truly sleeps. We've also discovered planets locked together in orbital resonance. In some star systems, planets don't move independently, they move in harmony. Orbital resonance occurs when planets' orbits align in precise ratios. One planet might complete 2 orbits in the same time another completes 3. This gravitational balance prevents collisions and stabilizes their paths. We see this phenomenon among Jupiter's moons, but exoplanet systems have revealed even more complex resonant chains involving multiple planets. These systems resemble cosmic symphonies, with each world following its own rhythm while remaining perfectly synchronized with the others. The balance is delicate. Tiny changes could disrupt everything. Yet for millions or billions of years, these planets hold their formation, orbit after orbit. The universe, it seems, is not only chaotic, but also profoundly musical. Some planets emit signals we still can't fully explain. Not everything we observe fits neatly into existing models. Certain exoplanets show strange, irregular changes in brightness, light curves that dim and brighten unpredictably. Others appear to be surrounded by rings, clouds, or drifting debris that cast uneven shadows. One famous case, Tabby's star, dimmed in such bizarre patterns that it sparked worldwide fascination. While natural explanations remain the most likely, the mystery endures. Some planets show extra dips in light before or after transits. Others appear distorted, as if trailing dust or wrapped in shifting clouds. We're learning to decode these patterns, but for now, they remain open questions, flickers of the unknown that invite curiosity rather than certainty. Some exoplanets follow orbits so extreme they nearly escape their stars altogether. Instead of calm, circular paths, these planets travel along stretched, elongated trajectories, swinging far into darkness before plunging back toward their stars like cosmic comets. At their most distant points, they receive almost no light or warmth. At their closest, they are briefly scorched by intense radiation and gravity. These journeys can take hundreds of years and are often unstable. Some planets were likely thrown into such paths by collisions or close stellar encounters. Others may one day break free entirely, becoming rogue planets drifting alone through interstellar space. These are cosmic exiles, barely held by gravity, dancing at the edge of escape. Their futures are uncertain, but for now, they continue to orbit, each pass a reminder of how dramatic and dynamic planetary lives can be. Some exoplanets even orbit the burned-out remnants of dead stars, white dwarfs. When a star like our Sun reaches the end of its life, it sheds its outer layers and leaves behind a dense, glowing core. Around these stellar embers, planets can still exist, circling faint remnants of once brilliant suns. These worlds endure in eerie twilight, orbiting stellar ghosts in silence, proving that even after a star's death, planetary stories may continue. These stars no longer burn with the energy of youth. They have exhausted their hydrogen fuel and no longer shine through active fusion in their cores. Yet they are far from cold or lifeless. White dwarfs remain intensely hot and luminous for billions of years, glowing with stored heat left over from their violent past. Around some of these stellar remnants, astronomers have discovered planets still quietly orbiting. Some of these worlds cling close, having survived unimaginable transformations as their stars swelled into red giants and later collapsed into dense embers. Others may have formed afterward, born from leftover debris that settled into new orbits long after the star's death. The environment is harsh. Radiation can be extreme. Gravity near a white dwarf is crushing beyond anything we experience. And yet, planets persist. Some may even orbit within narrow regions where temperatures could allow liquid water. These planets circle dead stars, but they themselves are not dead. They are survivors, echoes of former systems, proof that even after stellar death, planetary stories can continue. Some planets may have formed from the remains of destroyed worlds. In young and chaotic star systems, collisions are common. Worlds smash together, moons are torn apart, and entire planets can be reduced to drifting fragments. But destruction is not always final. From this scattered wreckage, gravity can slowly gather material once more, assembling new worlds from the broken remains of older ones. Astronomers have seen dusty disks around stars with ring-shaped gaps that hint at violent collisions or ongoing construction. Some exoplanets may be the exposed cores of once larger planets, stripped of their atmospheres by radiation or impact. Others may be patchwork worlds, fused together from fragments over immense spans of time. These recycled planets are not born pristine. Their surfaces may be scarred, molten, or uneven. Their orbits may be tilted or unstable, yet they exist, and they remind us that destruction is sometimes only the beginning of something new, stranger, rougher, and more resilient than what came before. Some exoplanets may have once belonged to entirely different star systems. While planets typically form around stars, stars themselves move through the galaxy. Over billions of years, close encounters, gravitational flybys, and chaotic interactions within stellar clusters can pull planets away from their original suns. Some worlds may be captured by passing stars, becoming permanent residents of systems they were never born into. These interstellar adoptees often follow strange paths, tilted, elongated, or unstable orbits that hint at a turbulent past. In some cases, their chemical makeup or motion suggests they don't quite belong. They are cosmic immigrants, transferred between stellar families by chance and gravity. Their existence reminds us that solar systems are not sealed or static. They evolve, exchange material, and sometimes welcome strangers from the stars. Some exoplanets may represent younger versions of Earth itself. When we observe distant worlds, we are not only looking across space, but across time. Some planets may resemble Earth as it was billions of years ago, when its atmosphere was thick with carbon dioxide or methane, and life, if present at all, was only beginning to emerge. These planets may still be forming continents, building oceans, or reshaping their atmospheres through volcanic activity and chemical reactions. Violent storms, shifting skies, and unstable climates could dominate their surfaces, just as they once did here. By studying these worlds, scientists hope to better understand Earth's own history. What did our skies look like long before oxygen filled the air? What storms rolled across silent oceans? Some exoplanets may preserve these answers, distant snapshots of an earlier chapter in the story of habitability, echoes of Earth before life learned to name itself. We have also discovered massive planets orbiting tiny, dim stars. Most stars in the galaxy are red dwarfs, small, faint, and incredibly long-lived. And yet, around some of these quiet embers, astronomers have found enormous planets, sometimes as large as Jupiter. At first glance, this seems unlikely. How could a small star host such a massive world? But nature often defies our expectations. In several cases, Jupiter-sized planets orbit stars barely a fraction the size of our Sun, often completing their orbits in just days. The contrast is striking. A colossal planet looming beside a dim, ember-like star. These systems challenge early theories of planet formation and remind us that even the smallest stars can host dramatic and complex planetary arrangements. Size, it seems, is not destiny. Some stars host entire families of planets, dozens of worlds crowded together. Our solar system feels orderly with its 8 planets, but other systems are far more compact and busy. Space telescopes like Kepler and TESS have revealed systems with 5, 6, or even 7 confirmed planets, often packed closer to their star than Mercury is to the Sun. In such systems, neighboring planets may appear as bright disks in the sky rather than distant points of light. Their orbits are finely tuned, often locked in resonance, moving together like gears in a cosmic machine. These tightly packed systems challenge our sense of scale and suggest that planetary architecture can take forms wildly different from our own. They hint that the diversity of planetary systems may rival the diversity of stars themselves. At the opposite extreme are systems with only a single known planet. These lonely worlds circle their stars in apparent isolation, with no nearby companions detected. We don't yet know whether these planets formed alone or whether siblings were ejected, destroyed, or simply too small for us to see. But the result is the same: a solitary planet tracing its path through space without the gravitational company of others. Such worlds may have experienced calm, stable histories or violent, chaotic pasts. Some are gas giants drifting on wide, slow orbits. Others are rocky planets clinging tightly to their stars. The skies of these worlds may feel vast and empty, shaped by silence rather than interaction. And yet, even alone, they endure, quiet witnesses to the many ways a planetary system can exist. No neighboring planets rise like moons. No gravitational dances synchronize the rhythm of the system. No planetary siblings tug and pull, shaping each other's seasons or orbits. Here, there is only one world and one sun, moving in quiet solitude through the vast expanse of space. The beauty is subtle, almost meditative, a single heartbeat in the immense, dark symphony of the cosmos. The isolation is complete, yet there is a strange elegance in this solitary rhythm, a reminder that even alone, a planet can persist, tracing its path through the silence of the void. Some exoplanets appear to be shrouded in thick, roiling steam. Imagine a planet whose surface is completely hidden beneath dense clouds of vapor. Not clouds like the ones drifting gently across Earth's sky, but layers of hot, thick, swirling steam. Some of these steam worlds likely orbit extremely close to their stars, where the intensity of stellar heat is enough to boil entire oceans, sending water into the atmosphere and creating a perpetual fog that blurs the line between ocean and sky. From afar, these planets might appear almost featureless, their surfaces invisible beneath the swirling mists. But beneath the haze, the environment is far from calm. Extreme pressures, searing heat, and chemical chaos churn in constant motion. Deep below, there may still be pockets of liquid water, or rocky surfaces that endure far beneath the vaporous veil. These are planets in a state of transition, where the distinctions between atmosphere and ocean, sky and surface, dissolve into a seamless, boiling whole. There are worlds where ice behaves like solid rock. On Earth, ice is fragile, easily broken and quick to melt. But on some distant exoplanets, under immense pressure and crushing depths, water can crystallize into exotic high-pressure ices, such as Ice 7 or Ice X. These forms are dense, rigid, and unyielding, behaving far more like stone than frozen water. Beneath thick oceans or inside massive icy super-Earths, these layers can form glaciers that move imperceptibly over eons or remain frozen and motionless for billions of years. Mountains might be composed of solid ice that never melts, and yet, hidden beneath these crusts, liquid oceans may continue to flow, warmed by internal heat trapped deep within the planet. Not all ice is made of water. On the cold, outer edges of planetary systems, temperatures drop so low that other volatile compounds, ammonia, methane, nitrogen, freeze into solid layers, forming exotic landscapes of pale blue, pink, or yellow frost. These alien ices may stretch as smooth plains, jagged ridges, or glittering fields, while some may slowly sublimate into thin, drifting atmospheres. Others could remain stable for billions of years, enduring as vast, frozen worlds where chemistry itself shapes the terrain. These planets, distant and quiet, are among the galaxy's most ancient travelers, their surfaces a testament to time and endurance in the cold, faint light of distant stars. We've also discovered planets in the densest, most chaotic neighborhoods of star formation, crowded stellar nurseries where hundreds or even thousands of stars ignite within vast clouds of gas and dust. For decades, astronomers wondered if planets could even survive in such violent environments. After all, the intense radiation, gravitational tugs from neighboring stars, and frequent stellar encounters could make planet formation impossible. Yet planets do exist here. They orbit while nearby suns blaze ultraviolet light across the sky. Some form rapidly and struggle to retain thick atmospheres. Others are flung from the system entirely, becoming wandering rogue worlds. Yet some endure, quietly tracing orbits among the brilliance of their clustered neighbors. Imagine standing on one such planet, the sky alive with countless stars, brighter and closer than anything visible from Earth. A bustling, dangerous neighborhood where even in the chaos, worlds find a way to survive. Some exoplanets formed in environments we once believed impossible. Early expectations imagined solar system-like arrangements. Rocky inner worlds, gas giants further out, gentle orbits, stable stars. But reality has been far stranger. Some exoplanets orbit binary or trinary stars, caught in the gravitational tug-of-war between multiple suns. Others circle pulsars, rapidly spinning remnants of exploded stars. Some emerge in metal-poor environments, where planetary formation was long thought unlikely. Each discovery proves one thing with certainty: nature is far more inventive than our theories. Planet formation is resilient, opportunistic. Where material exists, gravity will sculpt it. Dust grains cling together. Rocks collide and coalesce. Over time, even amidst cosmic violence or sparse outskirts, new worlds arise. They do not require perfection, only time, raw matter, and the patient pull of gravity. We've detected planets around stars only a few million years old, barely infants by cosmic standards. While stars themselves may live for billions of years, some planets begin forming almost immediately after stellar ignition. These newborn worlds often glow with leftover heat from formation, surrounded by disks of gas and dust. Dust grains collide and stick. Pebbles coalesce into rocks. Rocks accumulate into planets. Their orbits may still shift as they grow, and their atmospheres may be unstable or forming for the first time. Yet they are real. They exist. In these young systems, planet formation is no longer theory. It's an event happening before our eyes, unfolding in the light of a fledgling sun. Meanwhile, some planetary systems are older than Earth itself. While Earth formed approximately 4.5 billion years ago, we've discovered systems that have persisted for 10 or 11 billion years, orbiting their stars since long before our sun came into being. These ancient exoplanets have survived the slow march of cosmic time, weathering stellar storms, galactic tides, and the gravitational dance of their neighbors. They are enduring witnesses to the history of the galaxy, silent yet persistent travelers in the vast, ageless darkness. These ancient exoplanets have endured through unimaginable cosmic upheavals. They've survived galactic mergers, the violent outbursts of nearby stars, and billions of orbits around their suns, all without being destroyed. One remarkable example is the Kepler-44 system, which hosts 5 small, rocky planets orbiting a star more than twice as old as our Sun. Despite the immense age of this star billions of years beyond the lifetime of Earth, its planets continue to circle steadily, untouched by the relentless passage of cosmic time. These systems are living relics, time capsules from the earliest eras of the universe. Formed when heavy elements were scarce, they hold secrets about the conditions and materials available in the infancy of planetary formation. If life ever arose on these worlds, it could be unimaginably ancient, predating the emergence of life on Earth by billions of years. In a galaxy filled with such ancient, silent worlds, humanity is still just a newcomer, witnessing the quiet persistence of planets older than our civilization itself. Some exoplanets are giants beyond comprehension, with masses tens of times that of Jupiter. These supermassive worlds stretch the very definition of a planet, hovering on the boundary between planets and brown dwarfs, objects too small to sustain the fusion of stars, yet far larger than the planets we are familiar with. Many of these colossal bodies orbit far from their stars, retaining heat from their formation and glowing faintly in infrared light. Their interiors may contain dense cores of rock and metal, while others could be almost entirely hydrogen and helium, with atmospheres thousands of miles thick. The gravity on these worlds is immense, capable of shaping entire hemispheres into towering storms, and any moon orbiting such a planet could itself be large enough to sustain conditions for life. These titanic giants exist as slow-burning, quiet colossi, defying conventional expectations of scale and possibility. They are neither failed stars nor simply oversized planets. They are unique, awe-inspiring, and quietly dominant. In stark contrast, other exoplanets are extraordinarily dense, compact worlds capable of crushing iron beneath their surfaces. While some planets are light and airy, these rocky giants may have twice or more the density of Earth. To the eye, their surfaces might appear familiar: solid, cratered, perhaps mountainous. But beneath the crust, pressures rise to unimaginable levels. Iron itself could be compressed into exotic forms unknown on Earth, creating massive metallic cores and extraordinary gravity. These planets are often small in size yet incredibly heavy, the products of extreme formation histories or remnants of larger worlds stripped down by violent events. Walking on one would feel alien. The ground beneath would pull with unfamiliar weight, the very structure of the planet dense and unyielding. Such iron-rich worlds are stark reminders that not all planets are gentle, spherical bodies. Some are tightly wound, mysterious, and compressed into powerful, gravity-dominated objects. On the opposite end of the spectrum are exoplanets so light they could, theoretically, float in water. These puffy planets have enormous diameters but extremely low densities, often composed almost entirely of gas with only small, dense cores hidden deep within. Some are even less dense than wood, fragile giants suspended in the heat of their stars. These worlds often orbit close to their suns, where intense heat expands their atmospheres dramatically, forming thin high clouds and slow, drifting winds. They are massive yet delicate, more like bubbles than solid spheres, drifting gracefully through space under the gentlest tug of gravity, a striking contrast to the dense, iron-rich planets elsewhere in the galaxy. Not all planets retain their atmospheres over time. A planet's atmosphere is delicate, constantly threatened by stellar winds, radiation, or catastrophic impacts. Many small, rocky exoplanets orbiting close to their stars may have once possessed thick, life-supporting atmospheres, only to lose them billions of years ago. Observations reveal spectral fingerprints indicating little or no remaining atmospheric absorption. The causes vary. Some may lack strong magnetic fields to shield them, while others have been blasted by violent early stellar activity. Gradual erosion over eons can strip a planet down to its bare rock, leaving a silent, airless surface. These planetary ghosts bear the fossilized imprint of what they once were, orbiting their stars in solitude and reminding us that even planets are subject to the slow, inexorable forces of time. Some exoplanets, however, are still actively growing, gathering mass from the residual disks of gas and dust that surround young stars. Planet formation is not instantaneous. It can continue for millions of years. Observations with advanced telescopes have captured glimpses of these infant worlds, glowing in infrared light as they pull in gas, dust, and debris from their surroundings. Spiral structures, bright clumps, and gaps in these disks indicate the ongoing accumulation and shaping of planets. These young worlds may have turbulent, unstable atmospheres, surfaces still forming, and orbits that are shifting daily as they grow into mature planets. To witness these celestial babies is to observe creation in real time, a rare, almost sacred glimpse of worlds taking shape in the cradle of their parent stars. Destruction, too, is something we have witnessed in real time. Planets are often thought of as permanent, immutable objects, but in some systems we have observed them slowly vanishing. One candidate, monitored by the Kepler Space Telescope, displayed flickering and dimming patterns suggesting it was shedding material, leaving behind a trailing dust tail as it orbited its star. This planet, likely small and rocky, was gradually being eroded by intense heat, its atmosphere vaporized and swept into space. In another system, a sudden bright infrared flare hinted at the violent collision of two planets, producing debris and energy on a scale almost unimaginable. These observations are not theoretical. They are the evidence of worlds being reshaped, destroyed, and remade, a reminder that planetary existence is dynamic, fragile, and in constant flux. We are witnessing the final chapters of planetary stories unfolding in real time, a cosmic drama of creation and destruction, sometimes happening simultaneously. Some planets are born before our eyes, forming from swirling disks of gas and dust around newborn stars. Others vanish almost as quickly as they appear, destroyed by the relentless forces of their environment. Creation and annihilation exist side by side in the quiet machinery of the cosmos, a reminder that the universe is always in motion, always reshaping itself. Imagine a world covered not in familiar snow, but in shimmering metallic flakes. On Earth, snow is soft, light, and made of water ice, a comforting part of our seasons. Yet on certain hot gas giants, snow could be entirely different, composed of metals like titanium, iron, or aluminum oxide. High in the atmosphere, these metals exist as vapor, and as they cool, they condense into droplets that might solidify and fall as glittering, heavy shards. Aluminum oxide, for instance, could form high-altitude clouds that produce snowfall resembling tiny sapphire crystals. These metallic snows may never reach the surface, vaporizing as they descend, but in the upper atmosphere, they drift silently, creating a quiet shimmer beneath alien suns. Weather on such worlds is not shaped by water or clouds, but by heat, pressure, and elements we typically find locked in stone, a surreal, alien kind of meteorology. Some planetary systems are more like an intricate ballet than a chaotic jumble. Certain exoplanets are caught in tight gravitational dances known as mean motion resonances. In these systems, the orbits of neighboring planets are synchronized in precise ratios. For example, one planet completes exactly 2 orbits while another completes 3. These patterns aren't random. They are the result of billions of years of gravitational nudges, gently pushing each planet into a stable, repeating path. Such arrangements prevent collisions, stabilize motion, and allow multiple worlds to coexist in close proximity. The TRAPPIST-1 system is a perfect example, with 7 rocky planets orbiting a small star in near-perfect harmony. Each planet keeps time with its neighbors, a cosmic symphony ticking steadily across space. These orbital dances can endure for billions of years, preserved long after humanity itself is gone, a quiet testament to the clockwork precision hidden in the cosmos. Yet not all systems are so stable. Some appear precarious, with planets teetering on the edge of chaos. Gravitational simulations show that certain systems, while seemingly stable now, may unravel over tens or hundreds of millions of years. Planets could be ejected entirely, spiral into their stars, or collide catastrophically with one another. These unstable systems often result from chaotic pasts, migrating giants, close stellar encounters, or ancient disruptions. What we observe is just a snapshot, a momentary glimpse of order poised atop potential chaos, like a spinning top that has not yet toppled. Even the universe has fragile arrangements, delicate gravitational balances that may one day break, reminding us that planets, for all their size and apparent permanence, are never truly immune to change. Some exoplanets follow orbits tilted dramatically from the plane of their star's rotation. While most planets move in flat, disk-like planes, certain worlds orbit at sharp angles, sometimes even perpendicular to their star's equator. These tilted orbits often result from gravitational interactions with other planets, nearby stars, or ancient collisions. A planet born in the usual plane may be nudged, kicked, or flung into a new, tilted path. Such obliquity affects climate, seasons, and stability, but it also tells a story of cosmic upheaval. Tilt is a clue to a planet's history, a subtle lean that reveals dramatic shifts, violent encounters, and the unseen hand of gravity at work. Even stranger are planets that spin backward relative to their orbit, a phenomenon called retrograde rotation. While most planets spin in the same direction they orbit, some exoplanets rotate in the opposite direction. This reversal can result from collisions, tidal interactions, or gravitational encounters with other planets or stars. On these worlds, days are reversed, weather systems spin in unfamiliar directions, and sunrises and sunsets occur opposite to what would be expected. Standing on such a planet would feel subtly disorienting, the rhythms of light and time moving counter to the flow of the star above. These retrograde worlds are rare rebels, defying the rules of planetary motion and reminding us that the galaxy is full of surprises. Even without direct observation, we can measure the winds that sweep across distant exoplanets, and they are astonishingly fast. On some gas giants, winds exceed 500 miles per hour, enough to cross an entire continent in under an hour. These winds are driven by extreme temperature differences between a planet's day and night sides, particularly on tidally locked worlds where one hemisphere faces the star eternally, while the other is plunged in perpetual darkness. The resulting pressure gradients generate colossal jet streams, transferring heat from day to night, while storms circle the globe endlessly. Though invisible to human eyes, these atmospheric motions leave subtle fingerprints in the light we observe, a whisper of weather and turbulence from worlds light years away. Not all stars are gentle either. Many, especially young red dwarfs, unleash powerful stellar flares, sudden bursts of radiation thousands of times stronger than anything our sun produces. Planets orbiting such stars are constantly bombarded by intense energy, their atmospheres heated, stripped, or chemically altered. These flares can create spectacular auroras, sear planetary surfaces, and drive extreme weather patterns, further emphasizing that life, climate, and habitability on exoplanets can be unlike anything we experience on Earth. From metallic snow to chaotic dances, tilted orbits to retrograde spins, and winds faster than any terrestrial storm, the variety of exoplanets is staggering. Every observation reveals not just worlds, but cosmic stories, tales of formation, survival, upheaval, and resilience playing out across the galaxy. Each planet is a character, with its own history, personality, and rhythms, reminding us that the universe is not a static place but a vivid, evolving theater of creation and destruction, where even the quietest world is alive with motion, pressure, and possibility. Planets orbiting close to volatile stars can find themselves caught in a relentless storm, exposed to cosmic forces far beyond what we experience on Earth. These exoplanets are regularly bombarded by intense stellar activity, powerful flares of ultraviolet and X-ray radiation that can strip away atmospheres, molecule by molecule. If these planets possess strong magnetic fields, they might withstand some of the onslaught, creating protective shields that deflect charged particles. But without such defenses, the surface and atmosphere are vulnerable, exposed to the full fury of their star. Stars like Proxima Centauri flare dramatically, releasing energy thousands of times more intense than the strongest solar storms we've ever observed. For planets nearby, the consequences are profound. Could life survive such an environment? Could any atmosphere recover after repeated blows of searing radiation? Or would the surface remain a scarred, barren landscape, a testament to a sun too young and too wild? These flare-bombarded worlds remind us that habitability is not solely determined by distance from a star. It is also about the stability and temperament of the star itself. A planet orbiting within the so-called habitable zone may still be inhospitable if its host star is erratic and violent. Yet, elsewhere, some planets bask in the calm, gentle light of placid red dwarfs. Not all red dwarfs are tempestuous. Many burn slowly and steadily, emitting soft, consistent light for trillions of years. Around these quiet stars, planets can orbit close enough to receive sufficient warmth without enduring relentless stellar tantrums. These calm red dwarfs create some of the most promising habitats for life. Their habitable zones narrow but remarkably stable. Planets in such zones might be tidally locked, with one hemisphere bathed in perpetual daylight and the other locked in eternal night. Between these extremes lies the terminator, the twilight band, a narrow ring of eternal dusk and dawn where temperatures could remain moderate, winds gentle, and life, if it arose, might flourish over billions of years, untouched by the chaos that ravages other worlds. On some exoplanets, the skies may be ablaze with auroras that never fade. Unlike the fleeting northern and southern lights on Earth, these auroras could stretch across entire hemispheres, continuous rivers of green, blue, purple, and even red light dancing across the upper atmosphere. Especially on planets orbiting active stars or possessing strong magnetic fields, these auroral displays could glow not just at the poles but encircle the equator, creating a mesmerizing, permanent celestial ballet. On tidally locked planets, the contrast between a scorching dayside and a shimmering, aurora-lit nightside could be breathtaking. On giant gas worlds with enormous magnetic fields, these auroras might even be visible from space, painting the planet in luminous ribbons that ripple endlessly across the clouds. Such skies are alive, a continuous electric dance shaped by stars, magnetic fields, and charged particles. A spectacle impossible on Earth, yet commonplace on these exotic worlds. Some exoplanets host clouds unlike anything we know. On ultra-hot worlds, Rock itself can vaporize under extreme temperatures, rising into the atmosphere as silicate or metal gases, only to condense into clouds and rain-like particles. These mineral clouds, composed of silicates, aluminum oxide, or even compounds typically found in stone, create skies that shimmer with strange colors. Hazes of yellow, gray, or blood red, drifting across supersonic winds. The surface below may be molten, scorched, or pitted, while above, solid rock exists as clouds, suspended in a boiling, dynamic atmosphere. This is weather forged not from water, but from the very materials of the planet's crust, a reminder that the rules of meteorology are rewritten in alien conditions. Planets' orbits themselves are not eternal. Some worlds are slowly spiraling inward toward their stars, pulled by gravitational interactions and tidal forces. Year by year, their orbits shrink imperceptibly, like clockwork ticking toward an inevitable end. Over thousands or millions of years, these planets may eventually plunge into their stars, consumed in a final blaze of light and heat. We have observed hints of this process. Planets with decaying orbits, their periods shortening by fractions of a second, showing us that even celestial bodies that appear eternal are subject to the slow, inexorable pull of gravity. At the opposite extreme are planets cast outward, ejected entirely from their systems. These rogue worlds are flung into interstellar space by gravitational encounters with massive planets or passing stars, becoming cosmic wanderers. They drift alone through the galaxy, unbound and invisible, illuminated only by the faint glow of their residual heat. Some are as large as Jupiter, others more Earth-like, perhaps frozen solid on the outside, yet harboring hidden warmth beneath, powered by radioactive decay. Some may even sustain subsurface oceans, quietly flowing beneath layers of ice, invisible to the universe except for the faint signature of their presence. Rogue planets are ultimate wanderers, drifting in the void, carrying secrets that may never be revealed. Reminders that not all planets are tethered to stars. Some are free, eternal travelers of the dark. Even more extreme, some exoplanets traverse orbits so vast that they stretch across entire star systems, journeying for decades, centuries, or millennia in their elongated paths. These are worlds on epic odysseys, some approaching their stars only to retreat into frigid darkness, enduring extremes of heat and cold that dwarf anything experienced on Earth. Their orbits tell stories of gravitational tugs, cosmic encounters, and the restless energy of the universe itself. They are survivors, travelers, and storytellers, living proofs that planets are not static, serene objects, but dynamic worlds, shaped and reshaped by the cosmos, each carrying a unique history written in light, gravity, and time. Most planets orbit relatively close to their stars, moving in delicate harmony where light, warmth, and gravity maintain a subtle equilibrium. Here, conditions can be stable, allowing atmospheres to persist, oceans to remain liquid, and climates to develop patterns over millions of years. Yet, not all planets are content with a cozy orbit. Some exoplanets follow immense, sweeping paths, stretching across vast stretches of space on elongated, elliptical journeys. These wide-orbit planets can take hundreds, even thousands of years to complete a single circuit around their host stars. At their farthest reaches, they barely remain gravitationally bound, drifting on the edge of the star's influence, while at their closest approach, they swoop inward, bathed in intense starlight before retreating once again into the cold darkness of space. Such orbits are often the result of dramatic histories, planetary migration shaped by violent interactions with massive neighbors, gravitational nudges, or past collisions. In some rare cases, we've even spotted candidate planets orbiting hundreds of astronomical units from their stars, so distant that the star appears as a faint, glimmering dot in the sky, a solitary beacon in an almost empty horizon. These distant wanderers drift on the edge of their systems, tracing orbits as wide and slow as the passage of time itself, moving in rhythms that span generations, centuries, or millennia. Amidst the extremes, some planets occupy the cosmic Goldilocks zone, a narrow, precious region neither too hot nor too cold, where temperatures allow water to exist in liquid form on their surfaces. This region, sometimes called the habitable zone, is where worlds may maintain the right conditions for life as we understand it. Earth resides comfortably in this zone, and we've discovered a growing number of exoplanets in similar positions. Yet being in the Goldilocks zone alone does not guarantee habitability. A planet's atmosphere, rotation, magnetic field, and surface conditions all play crucial roles in determining whether life could exist. Still, these planets are among our best candidates for life. Whether rocky, ocean-covered, or wrapped in thick clouds, they bask in gentle starlight, balanced precariously on the edge of possibility. Even more intriguing are temperate exoplanets, where surface temperatures may closely resemble Earth's. These planets orbit quietly, receiving just the right amount of stellar radiation to prevent oceans from freezing or boiling. Their estimated equilibrium temperatures suggest the possibility of liquid water, moderate climates, and perhaps familiar weather cycles. Worlds such as Kepler 442b and TOI 700d fall into this category, presenting tantalizing possibilities for habitability. While we cannot yet know their true nature or the composition of their atmospheres, temperature provides a vital clue, a whisper that these planets might be more familiar than alien. Perhaps their skies are calm, winds gently sweeping over oceans, clouds gathering in the twilight, or rain falling in a soothing cadence. We can only imagine standing beneath such a foreign sky, feeling the warmth of an alien sun, sensing the subtle rhythm of life that could exist there. Weather on exoplanets can defy imagination. It is shaped by atmospheric chemistry, gravity, stellar energy, and planetary rotation. On some worlds, clouds may be composed of molten metal, while rain could fall as liquid glass or methane. Winds might howl at tens of thousands of miles per hour. On colder planets, snow could be made of ammonia, while hotter planets could see skies shimmering with silica dust. Lightning might leap across clouds of vaporized rock, and storms could rage for centuries. Some planets might have permanent jet streams, steady and unchanging, while others experience sudden, planet-wide weather upheavals triggered by flares or pulses from their stars. These are not Earth-like climates. They are weather systems sculpted by exotic physics, beautiful, terrifying, and utterly alien. Geological activity can also defy expectations. On icy exoplanets, volcanoes may erupt not with molten rock but with slushy mixtures of water, ammonia, or methane, so-called cryovolcanoes. Moons in our own solar system, such as Enceladus and Triton, showcase these icy eruptions, and it is likely that distant exoplanets host similar phenomena. Beneath frozen surfaces, hidden oceans may persist, warmed by internal heat and insulated by kilometers of ice. These subsurface seas could harbor complex chemistry or even primitive life, quietly stirring in eternal darkness. Cracks may open in the ice, slushy water may rise, and oceans may flow slowly beneath solid crusts, a hidden world of motion beneath a frozen exterior. Some exoplanets occupy the quietest corners of the galaxy, far from the bustling spiral arms or crowded stellar nurseries. These galactic suburbs are ancient, dim, and still, where stars drift slowly, radiation is low, and encounters with other stars are rare. Planets here enjoy long, stable orbits, uninterrupted for billions of years. In this cosmic shelter, life, if it exists, has time to evolve undisturbed, to adapt and endure. These worlds may be cold and distant, but in their tranquility lies a rare kind of stability, a gentle rhythm of existence where time itself seems to slow. In contrast, some planets speed through chaotic, densely packed starfields. Formed near the galactic bulge, in spiral arms, or within globular clusters, these planets exist in crowded neighborhoods where stars pass nearby frequently. Gravity tugs at orbits, nudges planets into new paths, and occasionally steals worlds entirely. For a planet in such a region, dozens of suns may dominate the sky, bright and close, constantly moving. The night never truly darkens. With beauty comes danger. A passing star might destabilize an orbit, or a nearby supernova could strip away an atmosphere. These planets live on the edge of chaos, navigating crowded, ever-changing stellar ballrooms. Yet they endure, orbiting their suns like dancers in a complex cosmic choreography. Among the most astonishing discoveries are planets orbiting pulsars, the dense remnants of massive stars that exploded in supernovae. These neutron stars spin rapidly, emitting beams of light that sweep across space like cosmic lighthouses. Around them, planets endure in extreme conditions, bathed in intense radiation from a dead star, demonstrating that planetary systems can survive, and even thrive, in environments that once seemed impossible, and no one ever expected planets to survive the most violent events the universe can throw at them. Yet astonishingly, some do. The first confirmed exoplanets ever discovered orbit a pulsar known as PSR B1257+12. Imagine a planet circling a star that is long dead, no longer producing energy through nuclear fusion, yet spinning dozens of times per second, pulsing like a cosmic lighthouse. These planets, small, rocky, and resilient, exist in the ghostly aftermath of stellar death. Their origin remains a subject of scientific debate. Perhaps they survived the destruction of the star that once nurtured them, enduring the supernova that created the pulsar. Or perhaps they formed afterward, coalescing from fallback material, the debris that failed to escape the pulsar's gravity, slowly gathering into new worlds. Regardless of their origins, these exoplanets are among the strangest known. Silent companions to a collapsed stellar core, orbiting a star that no longer shines with youthful fusion, but still pulses with the afterglow of death. They are planets around the dead, ghost worlds circling ghosts. Some planets endure even more violent beginnings. Supernovae are among the most powerful explosions in the cosmos, capable of outshining entire galaxies for brief moments and obliterating anything nearby. Yet, in rare cases, exoplanets survive such cataclysms. For example, in binary star systems, when one star explodes, its companion and any orbiting planets may remain, scorched and scarred but intact, continuing their celestial dance. Other planets may form afterward from the remnants of these explosions. Astronomers have detected heavy elements such as iron, calcium, and magnesium in the atmospheres of certain white dwarfs, silent evidence of planetary bodies that once orbited these stellar remnants. Any surviving planet would carry the imprint of catastrophe. Its surface seared, its air chemically altered, its environment forever changed, but it would still exist, a witness to both cosmic destruction and survival. Exoplanets also display atmospheres unimaginably different from our own. Earth's atmosphere is familiar, mostly nitrogen with traces of oxygen, water vapor, and carbon dioxide. But other worlds can be far stranger. Some are dominated by hydrogen and helium, like the massive gas giants in our solar system. Others are filled with methane, carbon monoxide, or thick clouds of sulfur-based compounds, creating skies of unfamiliar hues and chemistry. HD 209458b, for example, shows signs of escaping hydrogen, its bloated atmosphere slowly drifting into space. Other planets reveal the presence of titanium oxide, aluminum oxide, or exotic minerals in their upper atmospheres, shaping everything from temperature and light reflection to the weather itself. Some atmospheres are clear and transparent, while others are murky, dense, and choking. Some may appear deceptively calm from afar, yet conceal complex chemical layers beneath. Air, it turns out, is not always soft, blue, or gentle. On some planets, it can burn, shimmer, or carry the taste of metal. The composition of exoplanets extends even further. Some worlds may be rich in carbon, poor in oxygen, a stark contrast to Earth. These carbon planets could be dominated by graphite, diamond, and hydrocarbons, with mountains of pure carbon and oceans of methane. Their skies tinted with chemical compounds unfamiliar to human eyes. Others may have oxygen-poor atmospheres, iron-rich surfaces, or clouds composed of alien compounds. Life, if it exists, would operate under entirely different chemical rules, shaped by the local abundance of elements. These worlds challenge our assumptions about what a planet must be. Not every planet is an Earth analog. Some are built from different foundations, forged in alien chemical ratios, yet they are real, tangible places with their own chemistry, weather, and landscapes. Astronomers are now beginning the delicate search for biosignatures, clues that life may exist even across light years of space. On Earth, life has altered the atmosphere, creating combinations of oxygen, methane, and water vapor that are difficult to explain without biology. Using advanced telescopes, scientists are beginning to examine the spectra of distant exoplanets, looking for similar patterns. Clouds, temperatures, and star types all complicate the search, but some planets already show tantalizing hints. Traces of water vapor, unexpected carbon compounds, and atmospheric imbalances that could suggest biology. While we have yet to find definitive evidence, the search has never been more precise, and the possibility of detecting life on a distant world feels closer than ever. Some exoplanets are dominated by dust storms that rage for years. On Earth, dust storms are temporary, often ending with the passing of a season or a change in wind patterns. But on arid, dry exoplanets, dust storms may be nearly permanent. Winds sweep relentlessly across barren landscapes, lifting fine particles high into the atmosphere and keeping them suspended for years or even decades. The skies could glow copper, amber, or brown, sunrises and sunsets obscured behind thick haze. From orbit, these planets may appear smooth and soft, their geological features hidden beneath swirling clouds of grit. These storms influence surface temperature, chemical reactions, and atmospheric circulation. Any life there would not contend with rain or snow, but with endless dust driven by persistent, invisible winds. Other exoplanets reflect enormous amounts of light, shining brilliantly like cosmic beacons. Some are cloaked in silicate clouds, ice, or vapor that act like mirrors, reflecting starlight across the darkness of space. A planet like Kepler 7b, for instance, is believed to have reflective silicate clouds that glisten like polished gemstones. Others might have metallic surfaces or clouds of exotic compounds that capture and return light to the cosmos. These reflective worlds glow with borrowed starlight, visible from hundreds of light years away, acting as natural cosmic lanterns, casting their brilliance across the galaxy. In the extreme variety of exoplanets, from ghostly worlds orbiting dead stars to storm-tossed, dust-choked planets, from blazing reflective giants to chemically alien carbon worlds, the universe demonstrates that planets are not mere companions to stars. They are survivors, rebels, dreamers, and archivists of cosmic history. Each one carries a story of survival, adaptation, and unimaginable variety, challenging our understanding of what it means to be a planet and reminding us that the cosmos is far stranger and more beautiful than we could have ever imagined. Some exoplanets are dazzling in ways we could hardly imagine. Their albedos, the measure of how much light they reflect, are among the highest ever observed. In some cases, these planets can outshine their own stars in particular wavelengths, reflecting light back into the cosmos like distant cosmic mirrors. They do not generate energy themselves, yet they glow, shimmer, and shine as if illuminated from within. Brighter than Venus, brighter than fresh snow on a winter morning, these reflective worlds refuse to hide in the darkness. They remind us that light in the universe can be borrowed from stars, yet radiating beauty that captures our imagination. These planets shimmer not because they burn, but because they echo the brilliance of the stars that cradle them. Yet not all planetary systems are exotic or chaotic. Some resemble scaled-up versions of our own solar system, displaying a familiar cosmic rhythm that feels almost comforting. In these systems, smaller rocky worlds hug the inner regions, warmed by their star, while massive gas giants orbit further out, majestic and distant. Some include asteroid belts or icy outer zones, reminiscent of our Kuiper belt, showing that certain universal laws of planetary formation may hold across the galaxy. Gravity acts as the sculptor, arranging dust and gas into intricate patterns. Closer to the star, heat allows rocky planets to form. Farther out, gas giants condense from the cold. The result is a structure that feels familiar, an echo of home on a grander scale. Perhaps Earth is not as unique as we once believed. Perhaps the cosmic rules that shaped our solar system are at work elsewhere, quietly replicating their patterns in distant corners of the Milky Way. Even without moons, oceans, or life, these systems carry a comforting symmetry, a reassurance that the universe has its order as well as its chaos. And yet, many exoplanetary systems defy every rule we thought we knew. Some host gas giants orbiting closer than Mercury, scorching under their star's heat. Others follow tilted, elliptical, or even retrograde orbits, spinning opposite the direction of their rotation. Some stars boast more planets than we ever imagined possible. Moons may outsize entire planets, while planets themselves can migrate from their birthplaces, reshaping the architecture of entire systems. These extraordinary arrangements challenge the tidy models of planetary formation we once held dear. Perhaps planet formation is far more chaotic, opportunistic, and creative than we thought. Each new discovery expands the boundaries of possibility. Each planet tells a story of nature improvising, building worlds that defy expectation, daring us to reimagine what a planet can be. We are entering a new era in exoplanetary exploration, one where planets are no longer detected only through their shadows or the faint wobbles they induce in stars. Engineers and scientists are building telescopes designed to image exoplanets directly, capturing photons that have traveled across light years to reveal these distant worlds as more than dots or spectral blips. Instruments equipped with coronagraphs or paired with massive starshades to create artificial eclipses aim to block out stellar glare and isolate a planet's faint light. Telescopes like the Nancy Grace Roman Space Telescope, along with future missions such as LUVOIR and HABEX, promise the ability to not just detect planets, but to photograph them, study their atmospheres, analyze their light, and perhaps even search for signs of life. For the first time in history, exoplanets are becoming places we can see with our own eyes, distant worlds that might eventually be mapped, explored, and understood. Already, astronomers have achieved the first direct images of exoplanets. Using extreme precision, a handful of massive gas giants orbiting far from their stars have been captured in faint, blurry detail. The HR 8799 system, for example, provides a glimpse of 4 gas giants orbiting slowly over decades, their heat still radiating from formation. These images are crude, but they mark a turning point. Humanity has seen light coming directly from planets beyond our solar system for the first time. Though we cannot yet see continents, oceans, or clouds, we are witnessing the beginnings of a new age of observation. As instruments improve, so will our vision, eventually allowing us to detect weather systems, oceans, seasonal changes, and potentially even signs of life. The search for life in the universe often begins with planets. When we imagine extraterrestrial life, we naturally look for planets, places with air, water, sunlight, and geological stability. We examine their orbits, atmospheres, and the stars they circle. Every detection, every faint absorption line or spectral wobble provokes profound questions. Could this planet support water? Could it harbor microbes? Could something more complex exist there? Even the smallest hint sets off ripples across the scientific community because planets are the most likely abodes for life, the most tangible windows into cosmic biology. Exoplanets are our mirrors, our guides, and our laboratories, offering glimpses into the infinite ways worlds can exist and evolve. With each discovery, the universe reveals its creativity. Some planets are lava worlds, scorched and molten. Others drift alone as rogue wanderers, untethered to any star. Some are encased in icy rings or veiled in clouds of molten rock. Systems can be compact with dozens of planets in intricate orbits, or chaotic and scattered. Planets orbit dead stars, endure supernovae, and experience weather, chemistry, and gravity in ways that defy earthly intuition. Each new world expands our imagination, teaching us that the universe is not merely vast. It is inventive, unpredictable, and endlessly surprising. And these few thousand exoplanets we have discovered are likely only a fraction of the total. The cosmos is teeming with worlds, each one a testament to the boundless creativity of nature. By studying them, we learn to think bigger, dream further, and marvel at the unexpected beauty woven into the fabric of the universe. They may be more planets than stars in the Milky Way. For centuries, humans imagined planets as rare, delicate companions, tiny jewels circling distant stars here and there, almost incidental to the grand tapestry of the cosmos. But modern astronomy has shattered that notion. The evidence is overwhelming. Planets are everywhere. They are not anomalies, curiosities, or exceptions. The average star in our galaxy likely hosts at least one planet, and many stars hold multiple worlds. That means there could be hundreds of billions, perhaps even more, planets swirling in the Milky Way alone, each with its own orbit, its own gravity, its own silent story. Some are enormous gas giants, so vast they dwarf Jupiter. Others are small, rocky worlds, delicate as beads of stone. Some are scorchingly close to their stars, bathed in relentless light. Others drift at the frigid edges, frozen in eternal twilight. Many are unlike anything we could have imagined. And yet, this sheer number tells us something extraordinary. Planetary systems are not rare exceptions, they are the rule. The galaxy is not merely a field of stars. It is a vast, sprawling garden of worlds. Each planet follows its own path, tracing its orbit with quiet perseverance. Each one is a possibility, a chance for unique chemistry, unique climate, and perhaps somewhere among them the possibility of life. Among these countless worlds, some may be blue, some green, some golden with deserts we have yet to comprehend. Some may breathe, sustaining atmospheres rich in oxygen or alien gases. Some may be waiting, slowly forming, growing, evolving, their stories unfolding in silence, far from human eyes. Somewhere out there, among the billions, there may exist a planet like Earth, a rocky, warm, wet world capable of nurturing life. Perhaps it orbits a small, gentle red star, or maybe a bright yellow sun much like our own. Perhaps its oceans ripple beneath vast skies, forests stretch across continents, or life blooms in forms we cannot yet imagine. Perhaps it is quiet, only now awakening to the rhythms of its star, or perhaps it is ancient, with civilizations that rose and fell while Earth itself was still molten rock, yet we remain unaware. We have not found it yet, but the search continues. Every telescope launched, every observation made, every exoplanet discovered brings us one step closer to that distant twin. And when we finally locate it, that small, fragile, alien Earth, it will change everything. It will remind us that we are not alone in the vast, silent darkness, that other worlds exist, patiently spinning in their orbits, waiting to be known, to be understood, that the universe, in all its enormity, is not just a cold expanse. It is a place meant to be shared. And now our journey draws to a close. Tonight, we have wandered far beyond the warmth of our sun, past the edges of familiar skies, into a galaxy brimming with silent planets. Each world we've imagined is a quiet answer to the eternal question, what else might be out there? We have drifted across dust storms and molten skies, through oceans trapped beneath miles of ice, and through atmospheres made of vaporized metal, swirling gases, or alien clouds. We have watched stars flare and fade, witnessed planets flung into the dark reaches of space, and imagined life, strange, fragile, and impossible, taking root on worlds we may never touch. And through it all, one thought has endured. The universe is not only vast, it is rich with places shaped by gravity and weather, history and future, with stories still unfolding in the quiet. Each exoplanet we visited tonight, whether fully observed, theorized, or glimpsed faintly in distant starlight, is a world of its own. A tiny gravity well suspended in the immense sea of the galaxy. A question wrapped in silence, waiting for us to notice. And perhaps that is the wonder of it all. Even as you lie here, still and safe, the cosmos continues. Stars shine, planets spin, and somewhere, on a distant world not unlike our own, a planet may be turning slowly through its night, oceans reflecting alien moons, winds shaping landscapes in ways we can only dream of. So if your eyes grow heavy, if your breath slows into a quiet rhythm, if your thoughts drift like stardust through the darkness, know that you are already part of this universe. You are floating among the planets, already home. Thank you for sharing this moment, this quiet voyage among distant worlds. You are always welcome to return, to dream again, to wander once more among the stars. And if, by chance, you are still awake, there is always another video, another journey, another mystery waiting in the cosmos. But for now, rest. The planets will keep turning. The stars will continue to shine. The universe will wait. Good night.